have you ever stopped to think about what really keeps your body running smoothly? I mean, perfectly balanced, right down at the tiniest level. It's pretty amazing when you think about it. Like our body fluids, blood, the fluid around our cells, they live in this incredibly narrow Goldilocks zone for acidity. Not too acidic, not too alkaline. Just
Yes.
right. And why does this matter so much? Well, even a tiny, tiny shift can cause huge problems for, basically every cell. So today we're doing a real deep dive. We're going into the fascinating world of how our kidneys, and our lungs too, work together to maintain this super delicate acid-base balance. You've brought some amazing sources just packed with insights. Our mission here is to pull out every key piece of information so you walk away with a truly elite understanding, like professional level mastery of this stuff.
Absolutely. And it's a system that's, well, it's always operating right on the edge because the actual concentration of hydrogen ions, H plus UNDI, it's incredibly low compared to other ions. Think about sodium. It's about 3 million times more concentrated than H plus. Yeah. Which is exactly why we talk about pH, right? Using that log scale makes these tiny but critical numbers much easier to handle. And the core reason it's so vital is that pretty much every process in our cells, our tissues, our organs, it's all extremely sensitive to pH. Life just can't happen outside a very tight range. Plus, our bodies are constantly churning out acids and bases just from eating and, daily metabolism. So we need a really robust system to handle that constant load. It's essential for survival, really.
That really sets the stage. I mean, such low concentrations of H plus, it's so critical. It makes sense that it'd be a star player, right? So let's unpack that. Let's talk about the champion of this whole balancing act, bicarbonate. HCO3.
Exactly. Bicarbonate is, without doubt, the most important buffer in our extracellular fluid, the ECF. And just to give you a sense of its power, normal plasma bicarbonate is around 23 to 25 milliequivalents per liter. With an ECF volume of, say, 14 liters in an average adult, that means your ECF alone can buffer maybe up to 350 milliequivalents of hydrogen ions. That's quite a buffer.
That's a lot.
It is. But what really makes bicarbonate special, what gives it the edge over other buffers like phosphate, is that it's regulated by both the lungs and the kidneys. That dual control is key, and you can see why when you look at the chemistry. It's this reversible reaction. CO2 plus water makes carbonic acid, H2CO3. Then that carbonic acid breaks down into H plus and bicarbonate, HCO3.
Okay.
Now that first step, CO2 and water joining or splitting, it's actually the slower part, but there's an enzyme, carbonic anhydrase, that speeds it up massively. The second step, carbonic acid splitting into H plus and bicarbonate. That's almost instantaneous.
Okay.
So the critical thing here is that changes in either bicarbonate concentration or the partial pressure of CO2, the PiCO2, directly impact your body's pH. This whole relationship is summed up nicely by the Henderson-Hasselbalch equation. You don't need to memorize the formula, but conceptually, it tells you why pH changes when bicarbonate or PiCO2 changes.
So it links the lungs and kidneys directly to pH.
Exactly. It shows why they're locked in this constant dance. And it leads us right to the two main types of acid-base disorders. We call them metabolic, if the primary problem is a change in bicarbonate concentration, and respiratory, if the primary issue is a change in PiCO2. And here's the division of labor. Kidneys mainly control bicarbonate, lungs control PiCO2. That's fundamental.
Okay, fundamental. So going back to that daily load of acid and alkali you mentioned, that sounds like a constant challenge. Where does it all come from? Our food? Our cells?
All of the above, really. Our diet carbs, fats, proteins, and just normal cellular metabolism, they produce both acid and alkali. Even losing some alkali in our feces contributes. But for most people, especially if you eat meat, the net result, the overall balance, is an addition of acid to the body fluids each day.
Right, a net acid load.
Precisely. And we split these acids into two types. First, there's volatile acid. That's essentially just CO2, carbon dioxide. When things are working well, good blood flow, enough insulin, our bodies bring carbs and fats completely down to CO2 and water. We make a ton of CO2, like 15-20 moles a day.
Wow.
But our lungs are so good at getting rid of it that normally it doesn't really affect our acid-base balance. It's volatile because it becomes a gas.
Okay, so lungs handle that. What about the other type?
That's non-volatile acid. These are acids that aren't derived from CO2. Think things like lactic acid, sulfuric acid, hydrochloric acid. Where do they come from? Well, metabolizing certain amino acids from proteins like cysteine and methionine gives you sulfuric acid. Others like lysine, arginine, histidine, they yield hydrochloric acid.
So breakdown products mainly.
Mostly, yeah.
Right.
Now, it's not all acids. Some things we eat, like citrate or certain amino acids like aspartate and glutamate, actually end up producing bicarbonate. So that helps offset the acid load a bit.
A little bit of balance there.
A little bit, but usually the acid production wins out. Even things like phosphate in the diet can add to the acid load. And losing bicarbonate in stool is like adding acid. So when you add it all up, diet, metabolism, stool losses, you get this overall daily non-volatile acid addition. We call it net endogenous acid production, or NEAP. And typically for an adult, that's about 0.7 to 1.0 milliequivalents per kilogram of body weight per day. So maybe 50 to 100 milliequivalents total each day.
And that has to be dealt with.
Absolutely, because that NEAP consumes an equivalent amount of bicarbonate from your body, and that lost bicarbonate has to be replaced. And you see this clearly in clinical settings, like in diabetic ketoacidosis without enough insulin or with really poor blood flow, maybe during intense exercise or low cardiac output.
Right.
Cells can't burn fuel properly. They switch to making organic acids like lactic acid. That causes acidosis. But the flip side is, if you treat the underlying problem, give insulin, improve oxygen delivery, the body can then metabolize those accumulated organic acids. And that metabolism actually uses up H+ ions, helping to fix the acidosis.
Ah, so fixing the root cause helps reverse the acid problem too.
Exactly. Now, these non-volatile acids, they don't just float around causing damage immediately. Your ECF bicarbonate instantly buffers them. Bicarbonate gets used up, yes, but it prevents a drastic pH drop right away. But here's the kicker. Remember that 350 milliequivalents of bicarbonate in your ECF. If you're producing, say, 70 millieq of non-volatile acid a day and not replacing the bicarbonate used to buffer it, you'd run out in just 5 days.
5 days?
It is. It really highlights why long-term balance depends entirely on the kidneys generating new bicarbonate to replace what's lost. And that whole process of the kidneys getting rid of that daily acid load is what we call renal net acid excretion, or RNAE.
Okay, so this brings us right to the kidneys. They're not just filters. They're running this critical acid-base accounting system.
That's a great way to put it. In a steady state, NEAP, the acid produced, must equal RNAE, the acid excreted by the kidneys. NEAP just happens based on your life. The kidneys are the regulators. They adjust RNAE to match NEP, and in doing so, they generate that crucial new bicarbonate. But, and this is really important, quantitatively, that's not even the kidney's biggest job in this area.
What was big?
Preventing bicarbonate loss. Think about it. The kidneys filter about 180 liters of fluid a day, and that fluid has bicarbonate in it, around 24 mL2L. Multiply that out.
That's a lot, over 4,000.
Yeah, around 4,320 milliequivalents of bicarbonate filtered every day. Compare that to the 100 millieq needed to balance NEAP.
Okay, wow. So just holding onto the bicarbonate is quantitatively huge.
It's paramount. If the kidneys didn't reabsorb almost all of that filtered bicarbonate, we lose bicarbonate way faster than we could ever make it. And interestingly, both jobs reabsorbing all that bicarbonate and excreting the daily acid load are done using the same core mechanism, H+ secretion by the kidney tubules.
So secreting protons does both.
It does. But there's a catch. The kidneys can't make urine super acidic. The limit is about pH 4.0 to 4.5. Even at that maximum acidity, the amount of free H+ you can excrete is tiny, like 0.1 milliq per liter. Nowhere near enough to handle 5,100 milliq a day.
Okay, so how do they get rid of the rest of the acid?
They use urinary buffers, primarily phosphate, but also others like creatinine. These molecules soak up the secreted H+ state. The H+ bound to these buffers is called titratable acid, or TA. The name comes from the lab test you take urine and add alkali until the pH gets back to 7.4, the pH of blood. The amount of alkali you added equals the TA.
Clever. So you measure the buffered acid.
Exactly. But even TA isn't enough on its own. Which brings us to the second, and actually more important, mechanism for acid excretion.
Which is?
The synthesis and excretion of ammonium, NH4 plus Eric. This is a huge player because for every molecule of NH4 plus the kidney makes and excretes in urine, 1 molecule of new bicarbonate gets returned to the blood.
Ah, so that's the direct replacement for the bicarbonate lost buffering NEAP.
Precisely. It's the main way the kidney generates that new bicarbonate. So putting it all together, renal net acid excretion, RNAE, is basically ammonium excretion plus titratable acid excretion minus any tiny amount of bicarbonate that might escape in the urine.
God.
And normally, bicarbonate loss is negligible, so RNAE is pretty much just TA plus ammonium. And roughly speaking, TA is about 1/3, and ammonium is about 2/3 of the total. Ammonium is the real workhorse for net acid excretion.
Okay, ammonium is key. So we know what the kidneys need to do: reabsorb bicarb, excrete TA, and ammonium. But how do they actually do it? Let's zoom right into the cells of the nephron.
Okay, let's follow the bicarbonate first. Remember, almost all of that massive filtered load gets reabsorbed. The proximal tubule is where most of the action is, about 80 to 90%. Then the thick ascending limb of the loop of Henle grabs another 10% or so. And the last little bit, maybe 4 to 5%, is fine-tuned in the distal tubule and collecting duct. And it's all driven by H plus secretion.
Okay, so proximal tubule first. What's happening there?
Primarily, two transporters on the apical membrane, the side facing the urine, are pushing H plus out. The main one is a sodium-hydrogen exchanger called NHE3. It handles maybe 2/3 of the H plus secretion there, powered by the sodium gradient.
Okay.
The other is an H plus ATPase, basically a proton pump. Inside the cell, you have carbonic anhydrase making H plus and bicarbonate from CO2 and water. The H plus gets secreted out.
And the bicarbonate.
The bicarbonate gets transported out the other side of the cell, the basolateral side facing the blood, mostly via a sodium bicarbonate symporter called NBC1. So bicarbonate gets returned right back to the circulation. There are other helper molecules too, like carbonic anhydrase on the outside, water channels, but that's the core process. Even with all this H plus secretion, the pH in the proximal tubule only drops to about 6.5 because it's still pretty leaky to H plus and bicarbonate.
Okay. Leaky, but does the bulk of the work. What about the thick ascending limb?
Very similar mechanisms, actually. Also uses NHE3 as the main H plus secretor plus the H plus ATPase. Bicarbonate exits mostly via NBC1 again, and also another transporter, a chloride bicarbonate anaporter, handles about 10%.
Right. And the final bit, distal tubule and collecting duct.
Yep. This is where the fine-tuning happens, mainly by specialized cells called intercalated cells. There are two key types here.
Okay.
First, you have the H plus secreting ones, also called alpha intercalated cells. These guys are built for pumping acid out. They have powerful proton pumps on their apical membrane facing the urine, and H plus H's ATPase, and also an H plus K plus ATPase, which swaps H plus for potassium.
So pumping acid out, pulling potassium in.
Exactly. And the bicarbonate made inside these cells gets sent out the basolateral side into the blood, usually swapped for chloride. These are your main acid excretors in this segment.
Got it. Alpha cells secrete acid. What's the other type?
The HCO3 secreting ones are beta intercalated cells, and these are fascinating because they're basically set up in reverse.
Reverse.
Their H plus ATPase is on the basolateral membrane, pumping H plus towards the blood. And their chloride bicarbonate antiporter, called pendrin, is on the apical membrane, secreting bicarbonate into the urine.
Whoa. So they actively get rid of bicarbonate.
Exactly. They become more active when you have too much bicarbonate, like in metabolic alkalosis. They help you excrete the excess. But normally, the alpha cell's H plus secretion is dominant here. And here's a really crucial point about the collecting duct. Its apical membrane is very impermeable to H plus ulcis. It's tight.
Why is that important?
Because it allows the H plus that's pumped in to stay there. It lets the tubular fluid get really acidic, down to that pH 4.0, 4.5 limit. That steep gradient is essential for trapping ammonium and driving titratable acid formation. It wouldn't work if the H plus just leaked back out.
That makes sense. It concentrates the acid.
Yeah.
So we have these amazing cellular machines, but how does the body tell them when to speed up or slow down? How is it all regulated?
Great question. The number one regulator is simply the overall systemic acid-base balance. Your body knows if it's tending towards acidosis or alkalosis. Acidosis. The kidneys ramp up RNAe, more H plus secretion, more bicarbonate reabsorption, more acid excretion, alkalosis. They dial it back down. RNAe decreases.
But how do the kidney cells know? Are there sensors?
Yes, and this is really cool. The kidney cells themselves have acid-base sensors. They're not just passive responders. For example, there are specific receptors on collecting duct cells, like a G protein-coupled receptor called GPR4, that directly sense increased H plus in the ECF and trigger more H plus secretion.
Wow.
In the bicarbonate-secreting cells, there's another receptor related to the insulin receptor that gets stimulated by high ECF bicarbonate, telling them to secrete more bicarb. There are others too. An enzyme called soluble adenyl cyclase inside collecting duct cells senses intracellular bicarbonate. Even receptors in the proximal tubule can sense changes in PeCO2, triggering local angiotensin II production, which then boosts H plus secretion.
So the kidney is intrinsically sensing pH, bicarbonate, and CO2.
It seems so. It's quite sophisticated. And the response happens on different timescales. Immediately, changes in pH inside the cell can affect transporter activity directly or make H plus secretion easier or harder just based on the gradient. The cell can also quickly shuttle transporters to the membrane when needed.
Quick adjustments.
Right. And then for longer-term adaptation, like in chronic acidosis, the kidney actually makes more of these transporter proteins by changing gene expression. So you'll see more NHE3 in the proximal tubule, more H plus ATPase in the alpha intercalated cells, and maybe less pendrin in the beta cells.
Building up the machinery for the long haul.
Exactly. And beyond these direct cellular responses, various hormones and mediators fine-tune things. For instance, endothelin-1 ET1 production goes up in acidosis, and it helps insert more NHE3 and sodium bicarb supporters into proximal tubule membranes. Cortisol, the stress hormone, is also stimulated by acidosis and increases the abundance of those same transporters. Both ET1 and cortisol also boost ammonium production. Angiotensin II, which we mentioned being produced locally in the kidney in response to acidosis, directly stimulates H plus secretion in several segments and also ramps up ammonium production.
So the renin-angiotensin system is involved here too.
Definitely. And even parathyroid hormone, PTH, plays a role. Acidosis stimulates PTH, which then inhibits phosphate reabsorption in the proximal tubule.
Why would it do that?
Because more phosphate delivered downstream means more urinary buffer available in the collecting duct. It increases the capacity to excrete titratable acid. It's all interconnected.
That's brilliant. So it provides more buffer when needed. What about alkalosis?
The responses are generally the opposite, though maybe less studied in detail. RNAe goes down, less H plus secretion, more bicarbonate excretion, less TA and ammonium, and one more crucial layer. Factors not directly about acid base can still have a big impact.
Like what?
Volume status is a huge one. If your volume contracted, dehydrated, your body desperately wants to hold on to sodium.
Right, to restore volume.
And since sodium reabsorption is often linked to H plus secretion, especially via NHE3, volume contraction actually increases H plus secretion and bicarbonate reabsorption. This happens partly through the renin-angiotensin-aldosterone system. Ang2 and aldosterone both stimulate H plus secretion. Aldosterone also affects the electrical gradient in the collecting duct, making H plus secretion easier. Plus, changes in blood flow around the tubules enhance reabsorption.
So being dehydrated can actually interfere with correcting alkalosis.
Precisely. We'll come back to that clinical pearl. Also, potassium balance matters. Low potassium, hypokalemia, tends to stimulate H plus secretion, partly because H plus moves into cells as K plus moves out. High potassium, hyperkalemia, does the opposite, inhibiting H plus secretion. Especially in the collecting duct, low K plus increases the activity of that H plus past K plus ATPase.
Okay, so volume and potassium are major secondary influences. It's incredibly detailed. Let's circle back to something vital you said. Just reabsorbing filtered bicarb isn't enough. The kidneys have to make new bicarbonate. How does that work again?
Right. This is the net gain for the body. Two ways it happens. Excreting titratable acid and making and excreting ammonium. First, titratable acid excretion. Remember, by the time fluid hits the distal tubule and collecting duct, there's almost no bicarbonate left. So when those alpha intercalated cells secrete H plus here, it binds to buffers like phosphate. That H plus gets excreted, trapped on the buffer.
Okay.
But where did that secreted H plus come from? It was made inside the cell from CO2 and water. And when you make an H plus that way, you also make a bicarbonate ion. That bicarbonate then gets transported out the other side of the cell into the blood. Since the H plus left the body in the urine, this bicarbonate represents a net gain for the body. It's new bicarbonate.
Got it. So TA excretion and new bicarb generation.
Correct. But again, even with increased phosphate excretion during acidosis, this pathway alone usually isn't enough to cover the whole daily acid load.
Which brings us back to ammonium.
Exactly. The ammonium NH4 plus pathway is the major route for generating new bicarbonate, and it's highly regulated. It starts in the proximal tubule with ammoniogenesis making ammonia. The main fuel for this is the amino acid glutamine. Each molecule of glutamine metabolized in the proximal tubule cell yields 2 ammonium ions, NH4+, and another molecule called 2-oxyglutarate. That 2-oxyglutarate is then further metabolized, and the key result is the production of 2 molecules of bicarbonate inside the cell.
2 bicarb for every glutamine.
That's right. And these 2 bicarbonate molecules then exit the basolateral membrane into the blood. Again, new bicarbonate for the body.
Okay, you said the NH4+ has to be excreted for this to count.
Crucial point. If that NH4+ gets back into the circulation, the liver snaps it up and turns it into urea. And that urea synthesis process actually consumes bicarbonate. It completely undoes the kidney's work.
So getting the NH4+ into the urine is non-negotiable. How does that happen? It sounds complex.
It is a bit of a journey. After being made in the proximal tubule, NH4+ gets secreted across the apical membrane into the tubular fluid, mostly by hitching a ride on the NHE3 exchanger, substituting for H+H. Some uncharged ammonia, NH3, diffuses too.
Okay, so it's in the proximal tubule fluid.
Yes, but then, counterintuitively, a lot of it gets reabsorbed in the loop of Henle, especially the thick ascending limb. Here, NH4+ can substitute for potassium on that main salt transporter, the 1Na plus 1K plus 2Cl importer. It also moves between cells.
Reabsorbed. Why?
It seems strange, but this reabsorption causes NH4+ to build up to very high concentrations in the deep part of the kidney, the medullary interstitium. It creates a reservoir.
Ah, okay. A holding zone. Then what?
Then, from this interstitial reservoir, it gets secreted back into the tubular fluid, this time in the collecting duct. Collecting duct cells have special ammonia transporters, these rhesus RH glycoproteins, RHBG on the basolateral side, RECG on both sides. They primarily ferry the uncharged form, NH3, across the cell membrane into the lumen.
Okay, NH3 moves into the urine.
And as soon as that NH3 hits the acidic fluid in the collecting duct lumen, remember, the alpha cells are pumping H+ in there. It immediately picks up a proton and becomes NH4+ again.
And it gets trapped.
Exactly. That's diffusion trapping. Because, as we said, the collecting duct's apical membrane is pretty impermeable to the charged NH4++. NH3 can get in, but once it becomes NH4+ day, it can't easily get back out. It's trapped and destined for excretion.
That is elegant. Wow.
It really is. And it underscores again how vital that H+ secretion in the collecting duct is. If you inhibit H+ secretion there, you can't trap the NH3, NH4+ state. It cycles back to the blood. The liver makes urea, and you lose the benefit of the bicarbonate production.
So collecting duct H+ secretion is essential for both TA excretion and ammonium excretion.
Absolutely critical for both pathways of new bicarbonate generation.
How do doctors assess this ammonium excretion if it's hard to measure directly? You mentioned an indirect way.
Right, the urine-anion gap, or more accurately, the urinary net charge. You measure the main urine cations, sodium, potassium, and the main anion chloride, so Na plus K plus Cl. Normally in metabolic acidosis, the kidney should be pumping out lots of acid, mostly as NH4 plus Cl. Since NH4 plus is a cation we're not measuring in that formula, its presence makes the measured cations seem lower relative to chloride.
So the result is negative.
Exactly. A negative urine-anion gap during acidosis tells you the kidney is appropriately excreting lots of NH4 plus, as NH4Cl usually. If the gap is positive or zero, despite acidosis, that suggests the kidney isn't making or excreting ammonium properly, pointing towards a renal cause of the acidosis.
Useful tool. And how is this whole ammonium system regulated?
Also tightly linked to acid-base balance. Acidosis is the main stimulus. It ramps up the enzymes in the proximal tubule that break down glutamine. This takes a few days to fully kick in as new enzymes have to be made. Acidosis also increases the number of those RH ammonia transporters in the collecting duct, boosting secretion capacity.
Makes sense.
And remember, cortisol and angiotensin II, they also stimulate ammoniogenesis. Alkalosis, on the other hand, suppresses glutamine metabolism and ammonium production.
Okay. We've covered the buffers, the lungs, the intricate Kibben mechanisms. It's a lot. How does it all come together when our pH is actually challenged? What's the body's overall defense strategy?
It's a beautifully coordinated, multi-layered defense, all aimed at keeping that ECF pH between about 7.35 and 7.45. But remember, the key principle, these defenses minimize the pH change, they buffer the blow, they don't fix the underlying problem. Correction needs the root cause addressed.
Got it. Minimize, don't correct. What are the layers?
Line 1, buffering. This is immediate, especially the extracellular buffers like bicarbonate, phosphate, plasma proteins, takes seconds. Intracellular buffering also kicks in quickly, within minutes as H+ moves into cells and gets buffered by intracellular proteins, phosphate, and bicarbonate. Bone can also contribute, but more slowly, and chronic acidosis can leach calcium from bone. Okay,
immediate buffering inside and out. How does it differ for metabolic versus respiratory problems?
Good question. For metabolic problems, adding or losing non-volatile acid base, buffering happens in both ECF and ICF. Maybe 50–70% in the ECF, the rest inside cells. For respiratory problems, changes in PC2, buffering is almost entirely intracellular. CO2 zips into cells easily, changes intracellular pH and bicarbonate, which then affects ECF bicarbonate. H+ is buffered mainly by intracellular proteins.
Interesting distinction. Okay, buffering is line 1. What's line 2?
Line 2, the lungs. This is respiratory compensation, and its fast starts in minutes, maximal within hours. Your brainstem and peripheral chemoreceptors constantly sense PCO2 and H+. If H+ goes up, metabolic acidosis, they trigger increased ventilation. You breathe faster and deeper, blowing off CO2. Lowering PCO2 helps bring the pH back up towards normal.
Right, hyperventilation.
Exactly. And the opposite happens in metabolic alkalosis. Lower H+ reduces ventilation, PCO2 rises, which helps lower the pH back towards normal.
Hypoventilation. Are there limits?
Yes. You can only hyperventilate so much. PCO2 rarely drops below 10 millimeter Hg. And you can't hypoventilate too much without becoming dangerously low on oxygen, so PCO2 usually doesn't rise much above 60 millimeter Hg from compensation alone.
Okay, rapid but limited lung response. What's the third line?
Line 3. The kidneys. This is venal compensation. It's the slowest, taking several days to fully adapt, mainly because of the time needed to ramp up ammonium production. But it's powerful. In acidosis, the kidneys increase RNAe. They reabsorb all filtered bicarbonate and drastically increase titratable acid and ammonium excretion, generating new bicarbonate. In alkalosis, they do the opposite. They decrease RNAe by inhibiting H+ secretion, letting bicarbonate spill into the urine, and reducing TA and ammonium excretion. Those beta intercalated cells also get more active in secreting bicarbonate.
Slow, steady, powerful kidney response.
Exactly. Now let's tie this to that clinical example. Metabolic alkalosis from vomiting, complicated by volume depletion.
Right, the paradox.
The patient is clearly alkalotic, pH is high, bicarbonate is high. The kidneys should be dumping bicarbonate like crazy. But they can't.
Because they're prioritizing volume?
Precisely. The volume contraction activates the renin-angiotensin-aldosterone system. ANG2 and aldosterone plus the altered blood flow dynamics all conspire to increase sodium reabsorption, and with it, H+ secretion and bicarbonate reabsorption. So even though the body is alkalotic, the urine can become paradoxically acidic because the kidney is desperately trying to hold on to sodium and water, and that process overrides the need to excrete bicarbonate. The alkalosis won't get better until the volume deficit is fixed.
That really drives home how interconnected everything is. Volume status directly impacting acid-base correction.
So, given all this complexity, how do clinicians actually figure out what specific acid-base disorder is happening? What do the blood gas numbers tell them?
It boils down to a systematic approach using arterial blood gas ABG measurements combined with the clinical picture, of course. It's basically a 3-step process.
Okay, step 1. Step 1, look at the pH. Simple. Is it low? 7.35. That's an acidosis. Is it high? 7.45. That's an alkalosis. Since compensation is never perfect, the pH tells you the primary direction of the disturbance. Let's say you see a pH of 7.30. You know it's an acidosis.
Okay, acidosis. Step 2.
Step 2. Is it metabolic or respiratory? Now you look at the bicarbonate, HCO3, and the PCO2. Does the change match the pH? For our pH of 7.30, acidosis. If the bicarbonate is low, that fits with acidosis, so it's likely metabolic acidosis. If the PCO2 is high, that fits with acidosis, so it's likely respiratory acidosis.
So if HCO3 is low, it's metabolic. If PCO2 is high, it's respiratory for acidosis.
Exactly. Let's say our patient with pH 7.30 also has a low bicarbonate, maybe 15 MEQL, normal is 24, and their PCO2 is also low, say 30 millimeter Hg, normal is 40.
Low pH, low bicarb, low PCO2.
The low bicarbonate matches the acidosis, so the primary problem is metabolic acidosis. The low PCO2 must be the body compensating.
Oh, okay. That makes sense. Step 3.
Step 3. Analyze the compensation. Is the body's response appropriate? For every type of primary disorder, there's an expected degree of compensation. For metabolic acidosis, we expect the lungs to compensate by lowering PCO2. There are formulas or rules of thumb, like Winter's formula, that predict the expected PCO2 range. For our example, bicarb of 15, we'd expect a PCO2 around 30 millimeter Hg.
Which is what we saw in the example.
Right. So if the measured PCO2 falls within that expected range, we call it a simple metabolic acidosis with appropriate respiratory compensation. If the PCO2 was, say, normal or even high, that would suggest the lungs aren't compensating properly, or maybe there's a second simultaneous respiratory problem.
Okay, so check pH, determine primary driver, metabolic respiratory, check if compensation is adequate. Let's quickly define the simple disorders then.
Sure. Metabolic acidosis. Low pH, low HCO3, caused by adding non-volatile acid, like ketoacidosis, lactic acidosis, losing bicarbonate diarrhea, or kidney failure, can't excrete acid. Compensation. Lungs hyperventilate, low PCO2, kidneys increase RNAe eventually. And clinically, for metabolic acidosis, we often calculate the ammonium gap, sodium minus chloride plus bicarbonate, normally 816.
Right, the unmeasured anions.
Exactly. If the acidosis is caused by adding an acid whose anion is not chloride, like lactate, ketones, the bicarb goes down, but chloride stays normal, so the gap increases. We call this a high anion gap metabolic acidosis, HAGMA. If the acidosis is caused by losing bicarbonate, like diarrhea or adding hydrochloric acid, the body often retains chloride to compensate for the lost bicarb, so the anion gap stays normal. This is a non-anion gap metabolic acidosis, NAGMA. It's a really useful clue to the underlying cause. Remember to adjust for albumin levels too.
Got it. HEMA versus NAGMA. Okay, next.
Metabolic alkalosis, high pH, high HCO3, caused by losing acid, vomiting HCl, adding base antacids, or sometimes volume contraction, compensation. Lungs hypoventilate, high PCO2. Kidneys decrease RNAe, excrete bicarb.
Okay, respiratory ones.
Respiratory acidosis, low pH, high PCO2, caused by the lungs not ventilating enough. COPD, drug overdose affecting breathing. Compensation, kidneys increase RNAe, retaining bicarbonate, takes days, so chronic bicarb will be higher than acute. Respiratory alkalosis, high pH, low PCO2, caused by hyperventilation, anxiety, high altitude, certain drugs. Compensation, kidneys decrease RNAe, excreting bicarbonate, again takes days.
Simple disorders covered. What about mixed ones?
Mixed disorders are when you have two or more primary problems happening at once.
More complex.
Definitely. Example,
Nail the phone.
a patient with severe COPD, chronic respiratory acidosis, gets bad diarrhea, metabolic acidosis. Both problems are pushing the pH down. You'd see high TSO2 and low bicarbonate.
Okay, both contributing.
Or sometimes the pH might look almost normal, but the PCO2 and bicarbonate are way off in opposite directions, like an aspirin overdose. It causes metabolic acidosis, lowers bicarb, and stimulates breathing, lowers PCO2, causing respiratory alkalosis. The pH might be near normal, but the low bicarb and very low PCO2 tell you there are two processes pulling against each other. Analyzing the degree of compensation helps uncover these mixed pictures.
Fascinating how you can piece together the story from those numbers.
It really is. And if we just, zoom out for a moment, the big picture takeaways are pretty clear. First, the kidneys are the long-term guardians. They match RNAe to NEAP, mainly by reabsorbing filtered bicarbonate and excreting acid as titratable acid and ammonium. And crucially, both those acid excretion paths generate new bicarbonate for the body.
Okay, takeaway one. Kidneys' dual role in bicarb recovery and generation.
Second, the body's defense is layered. Immediate buffering, rapid lung compensation, and slow but powerful kidney compensation. 3 lines of defense working together.
Takeaway two. The 3 lines of defense.
And third, understanding the primary drivers is key for diagnosis. Metabolic means bicarbonate changes first. Lungs compensate fast, kidneys slowly. Respiratory means PCO2 changes first. Kidneys compensate slowly. Grasping that dynamic is essential.
Takeaway 3. Metabolic versus respiratory primary drivers and compensation patterns. Excellent summary. So, what does this deep dive mean for you? Listening and aiming for mastery. It means really appreciating this incredible physiological symphony. It's not just memorizing pathways, it's seeing how everything connects cells, organs, buffers, transporters, all working precisely to maintain life. Understanding it at this level, well, it moves you from just knowing facts to having real insight into how the body works and how it responds to stress. And maybe a final thought to leave you with. Given this constant production of acid and the body's elaborate defenses, think about this. What might be the absolute earliest sign, maybe even before pH changes much, that this delicate balance is being challenged? Could tracking something else give us a proactive heads up? How might that change how we think about health? Something to ponder. We definitely encourage you to keep exploring. Maybe look at some clinical cases now. With this foundation, you'll see them in a whole new light.